So now we want to use Ansys Workbench to solve that curved beam on their lateral loading. So we need static simulation, so we use static structural module here. And once it is loaded, we can first look at engineering data where we can see what material is available to us now. The material selected is structural steel. This is the right material for this problem. And next we need to create the geometry. So in order to do that, I'm going to use Design Modeler. So just wait for it to load. Now in Design Modeler, I'm going to sketch the center line, the neutral axis of the beam on the XY plane, and just to help with the sketching, I'm going to turn on the grid and I'm gonna change the major spacing to 1 meters. Next, I will choose this method to create the arc. So that is the center of the arc. This is the starting point. This is the end point. Next, we need to create the model. So we turn this into a model. First, we use concept to get lines from sketches. And second, we hit generate. So it generates the body. We need to define the cross section to be assigned to this neutral axis. So we have an I section. The dimensions were given in the brief. So W1 was 0.05 meters, W2 0.05, and W3, which is the height, 0.1. Thickness, this one was 0.0068, this one the same, and the last one was a bit thinner, 0.0045. Okay, we've got the cross section. We can now assign that cross section to the neutral axis. So here is where we do that. So this has been assigned. Just to see how it looks like, we can turn on the cross section solids. So we can look at our beam, and this is the section assigned to it, but you can see the orientation of the cross section is not correct. So we need to fix that, and in order to fix that, we need to rotate the reference axis of the cross section. How do we do that? We need to do that on the line object. So here on the selection filter, I choose this one, line edge. If I click on that line edge, I have this option here, so I can rotate the axis for this line edge. You can see that axis now is rotated. This green arrow is upwards now. And now if we look closely at our cross section, now this looks correct. Okay, perfect. So now we can leave Design Modeler and move to the next module, which is mechanical module. Well, by using the Design Modeler, we were able to define the geometrical characteristics of our structure. So this structure is now loaded here, and if I go to display, I can show the cross section here just to make it a bit look nicer. So we have defined the geometry, we have defined the material, we have defined the cross section. So these are all the information that is needed to form the element and then structure stiffness matrix. But in order to form the structure stiffness matrix, one other thing we need to do is to generate the mesh. Okay, so we need to mesh our structure with beam elements. Okay, so this is meshed. So you can see here all the elements. So these are more than 5 elements that we had. We can change this, so we can really insert sizing or insert numbers, for instance, to make this less or more elements. I just go with the default. And this is just a visual representation. So an element is really is a line with 2 nodes, but this line then has geometrical characteristic, which is the definition of cross section. So this has now been visualized for us. So next in static structure, I'm going to insert the boundary conditions. If you remember this node here, so I can select this filter. So this node was completely fixed. It means that its translational rotational degrees of freedom were 0. So I applied that here, and there was a force that was applied on this node at the end. So here I'm going to define the component of this force that is minus 10,000. And here the geometry selected. Perfect. So we are all set up. We have defined the boundary conditions, the known values. We have defined the known values of forces, external forces, and we can solve the problem now. So before I solve, I'm going to select a few outputs like total displacement, and I'm going to select the beam tool, which gives me different stresses in the elements. So now let's solve the problem. So essentially what is happening here is that the software is building the mathematical model. So essentially it's building the structure stiffness matrix, first element stiffness matrix, then structure by using the assembly procedure. And then it is inverting these matrices to find the unknown members of the vector of nodal displacements and then vector of nodal forces. Perfect. Now we have the solution, so we can look at the deflection of the beam. So this is in terms of meters here. So this 27 millimeters deflection, maximum deflection at the end, or displacement. What else we can look at is the direct stress. So you see it goes from a negative value to another negative value. Yeah, so this is in terms of pascals, the unit. So this is 9.3 megapascals, and this is 0.3 megapascals or negative. So direct stress is referring to the axial stress. Then you can combine the axial stress with the bending stress in the beam. So when you combine that, then you get the minimum combined stress or maximum. So I would say we are more interested in the maximum because that's what causes the failure in the structure. So the maximum here is happening at the root. This is what we're expecting, and the value is 281 megapascals, which is quite a large number. But we can look at the yield strength of this, the material we have used here, and check if this structure will fail under that load or not. So this concludes the solution for this problem. You will see later in the slides that we are discussing the effects of inadequate support. So for instance, you can free the rotations here and see what happens. So essentially the software cannot succeed. And that is what we call the singular stiffness matrix, which we should be aware of, and we should always make sure that we are avoiding it. So that is one of the common problems that happens when we are doing FEA simulations. I hope you have enjoyed this video. Thank you.